Hello guys, our topic today is going to be current, and current, what it is the movement of charges. When we've been talking about electrostatic energy, where just charges are stationary, they don't move. We looked at that in our lab, in the balloon lab that we completed. Okay, so charges don't move, they're stationary. We use Coulomb's law to figure out the electric force between those charges. Okay, but now we're going to look at charges that are actually moving, and what that is, or what we call that, is current. Okay, so current is just the rate at which charges flow through a conductor or through a wire when we start using circuits. So and current, the letter or the symbol that we're going to use for current is going to be I. And what current is just charges over time. Okay, or the number of charges that go through a certain spot in a wire in a certain time. So if you could count the charges that go through there, you would know the current. Okay. Now we know that charge, which is Q, and time, which is T. We know that charge is measured in coulombs. Okay, and we know that is measured in coulombs, and the time is measured in seconds. Okay. Now, what the units that we're going to use for current are going to be amperes, okay, or amps. And the symbol that we're using for that is going to be A, which is going to represent amps. So current is the rate at which charges flow through a conductor, and we can use the formula I equals Q over T to figure out the current if the only thing we have is the charge and the time. Remember that charge is in coulombs and time is in seconds, okay? All right, so conventional current. This is the type of current that we're going to be looking at when we're doing problems in electricity, okay? And what conventional current is, or what it states, is that this is the direction of that positive charges would flow. So in our circuits that we'll look at later on, or in our problems that we're going to be looking at electricity or charge that goes from the positive side to the negative side. Now, from the Bohr model, we know that the charge that actually moves is the negative and is not the positive, right? So you would think that the current would go from negative side to the positive side, but because of Mr. Ampere and the convention of our current, we're gonna stick with the idea that current actually flows from positive to a negative side of the battery. Okay. Now the electrons are the charges that move, not the protons, and we know that from the Bohr's model. Okay, so again, conventional current is just saying that you go from positive to negative. Okay, so that's current. Now there's different types of current. Okay, and we'll try to explain those to you. The first one is alternating current, and if we have a graph here, as you can see, current is in the y-axis and time is on the x-axis as seconds. And the first type of current is alternating current, meaning that it alternates. The direction of the flow of energy or charges alternate. Okay, they go back and forth. This is the type of energy or the type of current, sorry, not energy, the type of current that comes to your house from the electric companies. Another type of current is going to be your direct current, and this is current that does not alternate. It's just one direction. The electrons go in one direction. This is the type of current that Thomas Edison used when he started making his power plants back in the days, because I don't know the exact date, but when he started creating power plants, this is the type of current that he used to send to homes. But there was a problem with that. He lost a lot and lots of power, a lot of power over distances. So he would have to create power plants every, 2-3 miles to keep up with the demand. Okay. Now alternating current carries power over long distances without power loss, so you don't lose a lot of power, and that's the reason that we use alternating current to get to your home. And then once it's at your house, when you plug in a lot of your devices, you use AC to DC converters like in Macs. Okay, so that we can change that alternating current straight to DC current. And the reason we do that is because we cannot store alternating current, but we can store direct current. So batteries have direct current, and that's the reason we use AC to DC current, so we can charge up our batteries in our devices. Okay, so let's look at our example. It says a charge of 13,000 microcoulombs passes through a wire in 44.5 seconds. So we have the charge, we have the time, right? So A, what is the current on the wire? So we need to find the current. And B, how many electrons pass through the wire? Okay, so let's look at the current. First of all, we have to change microcoulombs to coulombs, because remember, our units need to be in coulombs. Okay, so our coulombs, or our charge, is actually 0.013 coulombs. Okay, and then the second thing we're going to look for is charge. Current. We know that current is charge over time. We plug in the numbers. 0.013 coulombs over 4.5 seconds, and that gives us 0.0028, repeating 8 amps. But if we use significant figures, then we're gonna keep, significant figures, we're gonna use 0.0029 amps, and that we get that from the 4.5, because when we divide, we keep the lowest amount of significant figures. So that's A. We know the amps, so we know the current. Now, if we know the current, then we're gonna look for the number of electrons. Okay, so the Q is given, and we have it in coulombs. So we gotta manipulate this formula so that we can find N. We have the charge is given. The elementary charge, which is E, is, you guys know that, 1.6 times 10 to the negative 16, and that equals 8.1 times 10 to the 16 electrons. Okay, so that's what we have as the electrons going through the wire. Okay, now the elementary charge is always going to be given, so just look for that on your problems. Okay, all right. The next thing, and here I write down the number of electrons so you can see how big of a number that is. That's the number of electrons that are actually going through the wire every second. Okay, all right.